Now, what's the last thing I want to do here? I wanted to give some thoughts about problem design to be stored in the back of your mind, I indicate here, okay? So randomization, when we're designing problems, it's very easy, well, not very true. It's mostly easy to create a problem that looks like a problem in a book, textbook somewhere. And it's mostly easy to add randomization so that the problem is then randomized for every student. This, generally speaking, works really well, and every once in a while you'll get something that either just really doesn't display the way you want it to do, or you end up with all sorts of weird errors that it's really hard to track down. And so this is just sort of trying to point out three things about that may or may not be helpful. Okay, so the first is, this is a really nice problem that you would expect to see in general. So I do problems with differentiation or integration, and you say, well, a really wonderful function to use this is the exponential. And so here I've done a sort of a sensible problem. I defined a to be a random variable from 2 to 20, and then I've said my solution is e to the a times x. And symbolically, this is a really nice problem. The way WeBWorK is going to decide if this answer is correct, however, is through numerical evaluation. And so it's going to actually be thinking about plugging values into this function to test whether it looks like the student's answer. And this becomes a major problem when you have things like number like 20 times x in the exponent. And so the default domain for the x is going to be negative 2 to 2, and so you could end up with e to the 400 or e to the negative 400. And completely reasonably, that's going to look very either irrationally big or irrationally small to for the numerical comparison. And so this will generate all sorts of, there'll be many answers that will be evaluated perfectly fine, and there'll be a few answers where you'll get it can't be evaluated properly, or answers that look like they should be wrong could be evaluated as correct because the numbers are too big. And so when you're thinking about defining variable or numbers and plugging them into formulas and things in the problem, it's worth stopping and thinking about what the size of the resulting calculations are going to be, and try to pick values that are going to be sort of moderately sized as you're doing it. The second thing, the purple box here, says, now suppose I'm defining a random variable and I'm computing an answer. It's very easy to end up with things that are symbolically, again, sort of sensible, but end up with very strange numbers in the answer. And so one thing that I generally try and do with mixed success is to try and get a problem where the answer the student has to type in sort of basically looks sort of nice. And very often, this is the point on the bottom one here. So the point on the purple box is then this answer here, if you pick a random number, if b is 9, right, then you're going to get a 9 over 70. And you're thinking, well, yes, 9 over 70 is a perfectly reasonable number, but it's not necessarily the nicest value you could ever come up with for the student have to calculate when they're putting it to the thing. And so often it's worth thinking about what's the answer that I want to come out, and then instead of randomly determining the parameters that you put in, sort of think about what the variation would be in the answer and go back and back calculate what the problem values should have been at the beginning, and make sure that both of those look reasonably nice. And so those are just sort of Gavin's thoughts about things that it's worth trying to do as we go and design more problems. And we'll talk about more of this type of thing as we continue in the workshop. Okay, awesome. Let's see, any questions at this point? Should I just go on this one? Okay, so my goal for the last part of this is to point out where there are problems, which is to say in the library, and a couple of observations about those when we're working on them. And so I want to go back and observe what we did in this exercise is we started with a sort of a template file and then started playing with it to end up with a bunch of different problems. And that's the way I edit problem files every time I'm editing them, is I just say, okay, let's try and start with a template and then plug in the stuff that I want to get the problem that I want. And another way to do this is to start with a file that at least starts with basically the same type of mathematics that you're looking at and edit that. And a good way to find problems that do that is to look in the library browser. And so I'm going to look in the library browser just for a moment and think about this. Right? So let's look at that. What does the library browser say? If I just want to browse, I can browse subjects. I'll pick single variable calculus. I'm going to pick, well, maybe if my mouse behaves itself, there it is, applications of differentiation. And I'm going to pick do, let's pick optimization of the natural and social sciences. There are 10 matching problems. That looks sort of reasonable. I'm going to click view problems and see what they are and see what we've got here. And so this is just showing me a bunch of problems. The path, let's just see, John showed us this on last time, and if you haven't seen it before, it's sort of handy to get a sense of where the problems exist in the library. And I'm actually purposely looking for one that's Michigan because those are ones that I wrote, and I have a good sense of what they're going to look like. And so this one is this. This is a relatively nice problem. I'm going to go over and say, well, what are my options? This uses math objects. Oh, look, I can edit it. Let's edit it and look and see what it looks like. First observation, this says this file is protected. That makes sense because it's actually in the library, and it would be bad if we could just arbitrarily edit things that are in the library. So if I wanted to actually use this as a template to work later, it suggests that I use a new version. And so I can click new version. Where do I save it to? And so the default is it's going to put it in this local directory, and then it has the same path as the library in the as it does in the actual problem library. The unattached problem means that it's not going to be part of a problem set. And so this would be a good way to save it in a place that I then wanted to play with if I wanted to look at it. For the moment, I'm going to ignore that because I'm not planning on editing it anyway. And so what I wanted to do is just take a quick look at the, oh, it's not letting me enlarge that thing. Quick look at the problem and see what it says. So the first thing I'm going to observe is the first section here looks like our description and tagging section that I pointed out. It's got a description. This is a problem from Hughes Calculus 4th edition originally. All of these things with the double pound signs are problem library tags, and so you can see that it's a calculus single variable problem, applications and differentiation. Here's our section. This was written at the University of Michigan by me. It's got a level which has to do with how hard it is. Static, I don't know what that is. Is it a static problem? It is a static problem. Static means that there aren't any actually variables in it. MO, math objects, it has math objects and so on. And then the title text tells you it's a problem from Hughes Chapter 4, Section 4.5, Number 5. It also appeared in 5th edition text in 4.4, Section 10, and it appears in the 6th edition text in 4.3 as number 32. Right, so, and it also appears in the Applied Calculus book in Section 4.3 of Problem 47. And so this tagging is just for the purpose of the problem library so that when you actually go searching for stuff, you can find it. The beginning, the initialization looks very much like what we had before. It has a document, it loads a bunch of macros, it sets a context. It's defining the begin problem text at the top here rather than a little lower. And then the other thing that is sort of funny is you look at this and you say, wait a minute, that doesn't look like PGML. And of course it doesn't because this is just a PG file. It doesn't include the PGML thing. And so in particular, I didn't load PGML up here in the load macros, and therefore I'm not using PGML when I come down here. And the one thing that you will notice if you start browsing through the library is very, very, very few of these use PGML. And you might ask, why not? And the answer is because PGML is not super, super new, but it was not super, super well publicized or documented. And so what we're doing in this workshop is we are starting with PGML because in a lot of respects it gives you the most command over the formatting of the problem, and it makes the association of answer blanks and answers more explicit and somewhat easier to manage. Most problems, almost all of the problems in the library are written using ideally math objects, in some cases not even math objects, and in old school or older style PG. And so when you look at this and you see begin text, it means it's just written in PG. And if you wanted to convert that to PGML, then you'll be changing a little bit of the delimiters for the equations. So instead of square bracket, single backtick, it uses slash parentheses. And instead of having an answer blank, which is the square bracket with underscores in it, it's defining it using this syntax with the answer rule. And we'll talk about that a little bit later in the workshop. For now, the main point is notice that there's this alternate format that exists, and we'll be seeing that later on, but we're going to spend most of our time starting with PGML because that has historically we found been easier to sort of get our heads around and figure out how to set up problems. The other thing, oh, this is a wonderful problem, look at that. The other thing is that this is an old school FUMCMP. So this is also old, an old answer evaluator, which we're going to see later as we go on. Oh, there's all sorts of things. You can tell this problem was written a long time ago. So when you look at these and you see that some of the stuff that is showing up in the problem doesn't look like some of the syntax that we're introducing you to, that just means that it was written long enough ago or using old PG, and we're going to cover the differences between those as we go through the workshop.